Okay, so welcome back to everyone. We're happy now to have Chris Akers, who will tell us about quantum minimal surfaces from quantum error correction.
Thank you. Thank you for the invite. I'm very excited to tell you all about this work in progress with Jeff Pennington. So so this is some work that is deeply connected to our paper from August. And so I hope to mention throughout exactly what the connections are. So first, quantum minimal surfaces, what are those? We don't usually say that phrase. So I just mean a restricted setting in which we would apply the quantum extremal surface prescription. So for example, if you consider the thermofield double, and you consider a slice like this that sits exactly at t equals 0, you can compute the von Neumann entropy, say, of some, so let's just consider the right CFT here, and here I've drawn a time slice for it, and then you consider some subregion of that boundary. You can compute the von Neumann entropy of that subregion B using this quantum minimal surface prescription with this bulk time slice. So here, you're using the bulk, and you only have to use this formula. You don't have to worry about extremality or the extra time direction at all. You just need to find the bulk region that minimizes the generalized entropy, this quantity. Good. So that's the prescription that we want to derive from quantum error correction. And what that's going to look like is a theorem of this form. So you don't have to understand this structure yet. I'm going to mention it many times before actually getting to it. But the idea is that we want the fact that, say, some bulk region little b is the entanglement wedge of capital B to be equivalent to some quantum error correction statement. And also we want to derive that it has the minimal generalized entropy. If you're thinking that this looks a lot like a theorem that Daniel Harlow proved in 2016, your mind's in the right place. And I'm going to be spending the first part of this talk actually telling you why that's not exactly what we want. We need something slightly different. So why do this? The basic motivation is that we want some sort of Hilbert space derivation of the quantum extremal surface or quantum minimal surface formula. So it's a very, I don't have to tell y'all that it's a very important formula for holography, but currently it's derived only from the Euclidean path integral, which is great, but it's sort of a black box that gives us nice answers that we like, but without telling us exactly why they're right. So this would be a way of understanding the quantum extremal surface formula. That's what we want. And this sort of thinking has already been very fruitful. So in this paper by Jeff and me from August, we use this motivation and this thinking to find that in certain situations, you actually are led to order 1/g corrections, like leading order corrections, to the quantum extremal surface formula. So in situations where you thought it worked, at least to leading order, it actually doesn't in some situations. And as a side benefit, like some side lesson that we learned, is that one-shot Shannon theory is very important to holography. So if you know what that is, great. So you can see why that's interesting. So that's the motivation. Let's start with the necessary background. So in 2016, Daniel Harlow taught us all how to understand the Ryutaki-Nagi and FLM formula from quantum error correction. So the setting was basically the following, and this will be kind of the setting used throughout this talk, even for our theorem. You have some isometry V. This is like the encoding isometry, and you have some set of input legs, which you should think of as like the bulk legs or the bulk degrees of freedom. And they are mapped via this isometry to some output legs, which you should think of as like the boundary degrees of freedom, like the CFT, the physical degrees of freedom of the code. And this isometry V can be perfectly general. So there's an example, a special case of this would be tensor networks, where you sort of break open this black box and you know exactly how the isometry is formed from like smaller tensors. So this is, but we don't want to just consider tensor networks. We're considering this more general setting of a general isometry where we don't know what's in the black box. So it was in this general setting that Daniel proved this powerful theorem that was basically the following. It's an equivalence between two statements. The first being that the output state takes a form that satisfies the Rita-Kinagi and FLM formula. So more precisely, it's what's written here in these parentheses, that for all states in the code subspace, so states on the set of input legs, that's like saying states in the code subspace. So yeah, the Hilbert space of the input legs defines the code subspace. Really, it's like that. It's the image of that under this isometry. So the statement is that for any state in the code subspace, V psi, it takes the form. It takes this form. So you can act two separate decoding unitaries, one on B and then one on capital B bar, that puts the state in this form where you have psi, which is the state you started with, the logical state, and then separately factorized from that is this chi. And this chi is some extra entanglement in the code, and it plays a very special role. So if you actually now take this state and you compute the von Neumann entropy of, say, capital B, what you're left with is two terms, just from the entropy of both of these factors. So one term is like the FLM or quantum correction term, and that's like the logical entropy. So this is like the entropy of the bulk state that in capital B's entanglement wedge, so to speak. And the other term is this extra entropy from the code. It's like the entanglement in this chi piece, and it has the interpretation of area. That was the main point of Daniel's paper. This condition is equivalent to some statement about reconstruction. So this reconstruction statement is written here. This is a sketch of it. And the statement is that for any operator O little b acting on some state psi, there exists an operator O capital B that sort of does the same job. And that's true for any state psi in the code subspace that you started with. And also the same is true of the complementary set of input legs B bar. So if there exists a little b such that this is true, then you know you have an RT formula and vice versa. That's the content of the theorem. Good. So that theorem is very nice. And there's a few questions, though, that it does not answer. So the two that I'm most interested in are these. So first, what is the meaning of the entanglement wedge of B? So that was answered in some settings by Daniel's theorem, but not in all settings. In general, Daniel's theorem talks about the so-called reconstructable wedge. And I'm going to explain this in great detail momentarily. And second, this theorem doesn't talk about minimality at all. So it shows that you get this area term, but it doesn't prove in any way that this is like the minimal area or the minimal generalized entropy. And that's something that we are interested in doing, and we will do. And as a side note, if you want to talk about minimality, you need to define, you need a definition of area that for all surfaces, not just one surface. So Harlow defined area for the RT surface. We're going to have to work a little harder defining some area for a general surface in a general code. So that will be what we do second before presenting the theorem, after talking about this. Good. So let me return to this point and expand on it. Consider this setup. So this is some ADS CFT setting where we have some subregion of the boundary, capital B. And let's say that what we know is that the bulk is in some state rho. And we also know that little b is the entanglement wedge of capital B in that state rho. What can you therefore infer about capital B's ability to reconstruct little b? So in other words, if you just know this, what does that imply as a quantum error correcting statement? So a naive guess would be that you just use Daniel's theorem, i.e. that B can reconstruct any operator on little b, and those operators should work for all states in the code subspace. But that's actually not true. So that is true in a limited setting, particularly exact quantum error correction with complementary recovery. But otherwise, it's not true. So in particular, in approximate quantum error correcting codes, that's generally false. That is not, you can't reconstruct all operators in the entanglement wedge in a way that works for all states in the code subspace. And we very much care about approximate quantum error correcting codes because ADS-CFT is an approximate quantum error correcting code. So to say that again, this all H code style reconstruction, so operators that work, that can be reconstructed and work for all states in the code subspace, that only works on what's called the reconstructable wedge, which is not the entanglement wedge. It is the intersection of entanglement wedges over all states in the code subspace. So in special cases, like exact quantum error correction with complementary recovery, all entanglement wedges are the same in the code subspace. And therefore, any particular entanglement wedge equals the reconstructable wedge. And the Harlow theorem is talking about the entanglement wedge. But more generally, yes.
Wouldn't it also be true in the approximate sense that for a sufficiently small H code, the entanglement wedge would coincide with the reconstructable wedge? Exactly.
Yeah. So exactly. So this, yeah, as you're pointing out, this is something that was known, by like all of these people that in certain limited scenarios, like small code subspaces, and the reconstructable wedge and equals all entanglement wedges. Yeah. So if you have a small code subspace, that's true. The reconstructable wedge and the entanglement wedge are always the same thing. But that's not always true. And so let me give you an example where there's a macroscopic difference. So here we have this setup where we're considering, again, some subregion B. And in the bulk, we have a black hole. And to be precise, our code subspace is defined as spanned by the set of energy eigenstates that lie within a certain energy band. And this energy band will be centered at some very large energy E naught. And the width of the band will be order 1. So most states in the subspace will be black holes. And in particular, the log of the dimension of the code subspace is going to be order 1 over G. And I'm going to dial the size of capital B such that the areas of these two competing extremal surfaces, these are the two competing extremal surfaces, their areas will be related as follows. So the area of gamma 2 will be bigger than the area of gamma 1, so that, if the black hole were in a pure state, the entanglement wedge would go all the way up to gamma 1. It would be B union B prime. But the difference is going to be much smaller than the log of the dimension, so that if the black hole is in a maximally mixed state, let's say in the code subspace, then the entanglement wedge only goes up to gamma 2. It's just little b. Then, as we just said, for pure states, the entanglement wedge is big. It includes B prime. But the reconstructable wedge, which does not depend on the state, will only be little b. It just depends on the code subspace, not any particular state. And because it's the intersection of all entanglement wedges over the code subspace, including mixed states, you in particular have to consider the maximally mixed state of the black hole, which has an entanglement wedge that only goes up to gamma 2. And so it turns out the reconstructable wedge in this setup is just little b. So the point of this example is that there can be a macroscopic difference between the entanglement wedge for a given state and the reconstructable wedge for that code subspace.
Quick question again.
Yeah.
Aren't there states in this code subspace that I can construct by taking careful superpositions of these E's that gives me a drastically different geometry or drastically different space-time, so that the notion of B is not well defined?
Yeah, I'm not ruling that out for sure. You're absolutely right. But what I need is that I just actually need to consider two states here to make the point I want to make, which is that I just need to consider a pure state with a very large entanglement wedge, and then this maximally mixed state, which we also understand with a very small entanglement wedge.
I mean, this you could even do with the dust cloud, right?
I could even do it with a dust cloud. Yes. Yeah. So I could replace this black hole with some dust. Maybe I'd have to take like a B that's 2 intervals on the boundary. Yeah.
I don't completely. So yeah. Sorry. May I ask a question? So I don't completely understand the distinction between entanglement wedge and reconstructable wedge. I would have thought that the entropy of the code should be included as as a mixed state when we are calculating the entanglement wedge. Is this wrong or?
Yeah. So in some sense, our theorem is going to give the sharp answer to your question. So I'm going to give a precise characterization of the entanglement wedge, which will be different from the precise characterization of the reconstructable wedge.
Okay.
So, yeah.
But maybe you can just say quickly, I mean, one issue is that if you have a code subspace, you can, with different states with different geometries, then you can have operators which are sometimes in the entanglement wedge and sometimes not in the entanglement wedge. And I think Chris is calling the reconstructable wedge is kind of the algebra of operators that are always in the entanglement wedge for all the states in the code subspace. But
right.
So that's in general doesn't include operators that might be in the entanglement wedge for some of the states.
Is the reconstructable wedge just the intersection of the entanglement wedges for everything in the code subspace?
That's right. Exactly. Yeah.
Yep.
That's the definition. Yeah.
Is there some reason why you're not phrasing this as a contrast, so that the current slide as a contrast between a large code subspace and a one-dimensional code subspace, the one corresponding to that special state?
You could think about it that like in the small. Yeah. So in the end, I want to be able to consider big code subspaces and still give a characterization of the entanglement wedge for any particular state. So including some mixed states that have like support on very many states, but maybe like small entropy. So I can't in general like restrict to a one-dimensional thing and keep the state exactly the same.
I see. So can I paraphrase that as saying that specifying a code subspace is a more restrictive thing because you're forced to sort of give equal weight in the mixture to every state? You want to be able to discuss states where that's not the case.
I would basically agree with that. I don't want to say that when you specify a code subspace. Actually, yeah. I agree with what I think you're getting at. Yeah.
Okay.
Yeah. So to summarize the points that I'm trying to make here, if all you know is that little b is the entanglement wedge of capital B, that implies something weaker about reconstruction on little b than the all H code reconstruction.
Sorry, I have a question.
Yeah.
So here it sounds like the reconstructable wedge depends on the definition of a code subspace, right? You can choose it to be super large, then this two will be the same. I mean the reconstructable wedge will be same as the entanglement wedge.
If you choose it'll be different. Yeah. So if you make the code subspace very big, the reconstructable wedge becomes different from the entanglement wedge.
Oh, okay. So what is the criterion for you to choose a appropriate code subspace for ADS-FT, or it's very arbitrary?
Yeah, I would say it's arbitrary. You can, consider what,
That, and then the entanglement wedge does not rely on how do you choose a co-subspace, right?
That's right. That's right. Exactly. That's another way to say it. Yeah. So the reconstruction we're looking for is something weaker than this all H code reconstruction, right? Because that was very strong. It required that B was in the entanglement wedge for all states in the code subspace, not just one state. So to give the logical structure, the reconstruction that we're used to talking about was, satisfied this sort of equivalence, that if you could do that reconstruction on little b, then little b was the reconstructable wedge, which was a feature of the code subspace. We want something else, something that will turn out to have to be state specific. And what the point of this work, the theorem, will be an equivalence between some region being the entanglement wedge for that given state and a specific sort of quantum error correction with respect to that state. So this state-specific sort of reconstruction is sometimes called subspace dependent because it depends on the subspace of H code. And this all H code style reconstruction is sometimes called subspace independent because it does not depend on the subspace of H code that you're talking about. Just if you've heard those terms, it's connected that way. So what is the sort of state-specific weaker sort of reconstruction that we're looking for, or that is in our theorem? I'll just flash the answer and I'll explain it in more detail when I actually present the theorem. But it's this. So first of all, you're not able to reconstruct all operators. You're able to reconstruct product unitaries. This is what you're guaranteed. So these are unitaries in the bulk that factorize across different bulk points, or unitaries on the inputs of the isometry that factorize across the inputs. And in particular, so this is the statement of reconstruction that for such a product unitary on little b, there's a unitary on capital B that does the same job. It's not this unitary on capital B that does the same job is only required to do the same job acting on psi. It doesn't have to do the same job acting on any code subspace state. So this UB is psi dependent. I'll expand on that. But the reason why product unitaries are the things showing up here is basically because these are operators that don't change the entanglement structure of the bulk. And so they don't move the position, they can't move the position of the quantum extremal surface, which is a very desirable feature if you're talking about reconstructing them. Like if you could reconstruct an operator that then moves itself out of the entanglement wedge, therefore you wouldn't have been able to reconstruct it, you run into problems.
So these are rather singular operators from the bulk point of view, right?
So from
like if you had a lattice, they would have to be product operators at the lattice scale. It's a little bit unsettling.
That's right. They'd have to be, yeah, exactly. I'll have more to say about that. But from like this general code point of view, it's like they're totally sensible. But for algebras, maybe there's more you have to do. Okay, so now that I've defined this sort of reconstruction that that is going to be equivalent to the entanglement wedge, that is going to be guaranteed by being in the entanglement wedge, I need to define for you a definition of area that works for general surfaces and general codes. And the reason is that the entanglement wedge is strongly state dependent. So given a single code subspace, we need to talk about the area of not just one surface, but many surfaces. Okay, and a side benefit will be that this will allow us to compare the generalized entropy of different bulk regions, and therefore prove minimality of the entanglement wedge. Before I can give our definition of area, I need to define a special sort of state called the Choi-Jamalkowski state. And this is a mapping, this is a state you might be familiar with. It's a particular way of taking some operator, like the encoding isometry, and defining an entangled state. So the idea is that given our isometry V that maps from the input legs to the output legs, you define the Choi-Jamalkowski state, which is a state on the output legs union some reference, as follows. Take a maximally entangled state between the inputs and the reference, and you act the isometry, which of course just maps these input legs to the output legs. Okay, and then so pictorially that's like this. You just took this maximally entangled state, took half of it, put it into the isometry. The other half you kept around for the output state, and then what you get on these output legs, that the state there is the Choi-Jamalkowski state. So it's a very special state, and with it I will define area for general surface. Here's the definition. So the area of some set of input legs little b, so say these are the input legs whose area you want to compute. Subscript b, which I'll explain, you have to include a part of the output there, because you have to actually enforce homology with that part of the output, enforce what can be interpreted as homology. This is defined as a certain von Neumann entropy in the Choi-Jamalkowski state. So if you want to compute the area of little b, you have to take the part of the reference that purifies that part of the input and compute its von Neumann entropy unioned with b. Okay, so why this area? There's a few reasons. So one, it satisfies like the basic things that you would want an area to do, and that's like not too hard to see. So for example, in the context where like Harlow gave a definition of area, this agrees with that. So in his context, where like say B is the entanglement wedge of big B, in this von Neumann entropy, the reference will purify the logical part, and then all that's left in this entropy is just the entropy of the chi part. So this will just be the entropy of the chi part of B, which is what he called the area. You know, another argument you might make for this to motivate this is like, what else could it be? You know, there's a very limited set of options for it that would work for general surface for general code. It's possible that none of them would work, but it turns out that this one does, and in fact has a lot of unique properties that make it the preferred choice. Let me comment on the fact that when defining the area of a bulk region, we don't usually have to specify a boundary region. But here, B shows up very explicitly. Let me just say that that is like enforcing homology with B and leave it at that, but I can explain more at the end. Okay, so given that definition of area, let me show you the theorem. So the theorem is in the same setup that we've been using, and I'm going to present what is the exact version of the theorem, so the exact quantum error correction setting. That is not the most interesting case because it's basically just already handled by DHW and Harlow, etc. But the approximate theorem exists and is very similar. It's just uglier to write. So there's an approximate generalization of what we have, but it would have been very difficult for you to parse if I wrote that. So the idea of the theorem is first define, so you have this isometry, and then we're going to consider some subset of the input legs to be little b, some subset to be little b bar. And we're going to define product unitaries, as I said before, which are just unitaries that factorize across these inputs. And moreover, we're going to consider some arbitrary state on the inputs. And that arbitrary state can even be mixed. And in that case, you purify it with a reference. And so in general, we're going to consider some pure state on the inputs union a reference. Then the theorem says that the following two conditions are equivalent, and moreover, that they both imply this third condition. So the first is the simple statement that little b is the entanglement wedge of capital B. And so this is the familiar part of that. It turns out that to really nail down that it's the entanglement wedge, and that you're not just, it turns out you need to include this for all product unitary statements, which I can go into more detail about. And before I explain 2, which is like kind of the real meat of the theorem, let me explain 3. So you can use these to imply that for any other set of input legs, that set of input legs will have greater generalized entropy than the entanglement wedge. So that's a desirable feature. 3 is not equivalent to 1 and 2. It cannot be. There are just counterexamples in general. And this was one of the main points of Jeff and my paper from August. So the main point there, one of the main points was that just finding the minimal generalized entropy surface does not give you the region of the bulk whose generalized entropy gives you the von Neumann entropy. That's just not true in general. It is in special cases. Okay, so the quantum error correction condition that is equivalent to little b being in the entanglement wedge of capital B is this one with product unitaries. So to spell it out, the statement is that for all u little b, there is a u capital B that sort of does the same job acting on psi. And the same is true for u little b bar. There's a unitary acting on capital B bar union the reference that does the same job. That's the statement. This is a little bit like being able to do reconstruction of many different two-dimensional subspaces, right? Like you take psi to some other state, and you can reconstruct within that subspace, that two-dimensional subspace. That's a little bit like what this is saying. So it's, but notice that again, this unitary is allowed to be strongly psi dependent. And so it's not like this reconstruction has to work for the entire code subspace. Just like, it just has to be the case that you can do this for each psi. Sorry, for each u acting on this one psi. Let me quickly explain a perhaps curious feature, which is the fact that this statement of reconstruction here has to include this reference. So that's like, like the Harlow theorem did not, it looked a little bit like this. This is different because it's more state dependent. It's only about product unitaries, etc. But also we include this R here in the reconstruction of little b bar. That's for the following reason. No man's lands. So no man's lands, I'm going to define as a region of the bulk that neither capital B nor capital B bar can reconstruct. And there's 2 types. There's the type that I think that most people are familiar with, which is exemplified by taking a maximally mixed state of the black hole. So this is the same setup that I described earlier, where if you take the maximally mixed state of the black hole, the entanglement wedge of capital B goes up to gamma 2, and the entanglement wedge of capital B bar just goes up to gamma 1. And in this case, you can say that neither B nor B bar have any information about B prime. So in particular, neither can reconstruct B prime. And what's special about type 1 no man's lands is that the entanglement wedge of B is still well defined. Like you can still use the quantum minimal surface prescription in such a setup. But there's a separate sort of no man's land, which I'm calling type 2, which were identified by Jeff and me in our August paper. And this sort of no man's land arises if you took the setup, but instead of a maximally mixed state here, you put in like a mixture that's half the maximally mixed state and half a pure state. And in this case, what you have to say is that still neither B nor B bar can reconstruct B prime, but that's because both have some information about B prime. It's not that both have none, it's that both have some. So the other one can't reconstruct it. And in this case, the entanglement wedge of capital B is actually just not well defined. Because, for example, if you tried to compute the von Neumann entropy of B, capital B, it wouldn't be given by the generalized entropy of any particular bulk subregion. It would be like, you might want it to be the generalized entropy of little b, but it'll also know something about little b prime. So any entropy in little b prime will, say, contribute to the entropy of capital B. So the reason we have to include R in condition 1 is because it basically allows for no man's lands, but only of type 1. If it like forces B to know nothing about B prime. So this is condition 1 written again. It forces B to know nothing about B prime. If you have type 2 no man's lands, then just like neither 1 nor 2 are satisfied, and that's fine. So I won't, okay. So that sort of explains the theorem and what it's saying. And so here's a sketch of the proof that I'm going to flash before you. And I'm happy to go into detail, like explaining the sketch of the proof, but maybe I'll leave that for the question period. But basically each of the directions, yeah, has sort of a different flavor. And let me now tell you the upshot and some interesting future directions. So the upshot was that the quantum minimal surface prescription is equivalent to a certain state-specific sort of reconstruction. It was like this. So if all you know is that little b is the entanglement wedge of capital B, then you're guaranteed this sort of reconstruction. If you knew the stronger thing, that it was the reconstructable wedge, then you'd be guaranteed a stronger sort of reconstruction. I showed you the exact theorem, but we also have the approximate theorem, which is I emphasize because the approximate version is sort of the more interesting case. So it's good that we have that. And it's done, but we haven't nailed down like the epsilons and deltas. The algebraic version is in progress. There's some interesting subtleties there, like what Daniel was hinting at earlier. Yeah, I won't expand on that for now. Another interesting future direction is understanding the meaning of this definition of area in gravity. So it works for codes, but so you would expect it to have some physical meaning in gravity, and I expect that it does. And it might help us with some open problems, like giving a physical interpretation to the area of non-extremal surfaces. And that's an idea that I first heard suggested by Netta like a little more than a year ago. So I think that's a very interesting thing to think about. And finally, now that we've given the full quantum information theoretic understanding of quantum minimal surfaces, the next step is to understand extremality, which I think is a very important step, because understanding that may actually explain why this open problem about time and the quantum error correcting code, which is currently very poorly understood. So for example, this is something that Aaron Wall once explained to me, but any errors in what I say is of course mine. So if you have a state like this, quantum error correction works very well relating this bulk state to this boundary state. And in GR, of course, this bulk time slice is equivalent to the time slice like this. They're just related by some sort of gauge transformation. But in quantum error correction, this time slice is no good. So we could use this one, everything works very well, but this one we just can't make sense of with quantum error correction at all. And that's a very interesting subtlety, and understanding how extremality arises in this prescription, I think would be the key to understanding that. Thank you.
Okay, so we have time for questions. So go ahead, Matt.
Hi, I just wanted to make a comment about that very last point. I'm not sure how relevant this comment is, but of course there won't in general exist any time slice that works for all choices of boundary regions, even on a given boundary time slice.
Yeah.
So is that a feature or a bug? I mean, yeah. Wouldn't we have expected there, in this quantum error correction story, for there to exist a single code, that it describes the whole bulk or something like that?
I think that a complete quantum error correction understanding would describe the whole bulk and like solve the problem you're talking about. Mm-hmm. And there's like a problem even before you start considering other subregions. That even for this same particular subregion, yeah. Here, this time slice doesn't work.
Yeah. But what I'm saying is, even once you've solved that, then you're going to run into trouble with a different region or whatever.
Yeah, it's not 100% clear to me if they're going to be disjoint problems. They might be related because they're both about like constraints in the bulk. So, yeah. But I agree with your problem.
If we believe in maximum, don't we always think there'll be some slice like this for any state?
Yeah, for a given boundary region, yeah.
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 Okay, Edward.
So in your theorem, if I understand correctly, you said that you talked about optimizing overall decompositions of the bulk as B prime. But was this literally meant to be all tensor decompositions of the bulk code Hilbert space as B tensor B prime? Or was there a preferred, was it local? Was there a preferred class of allowed decompositions, which was actually suggested by the way you wrote about your product unitaries?
Good, yeah. So the way this theorem is structured is, yeah, there is this preferred decomposition.
So it's
whether or not, yeah,
so the preferred decomposition, you've written it here, where you wrote product unitaries.
that's right.
Like
Yeah,
products over qubits or some other elementary things.
exactly.
And your minimality was over all decompositions suggested by that.
Exactly.
Okay, thank you.
And the strongest statement, Edward, that you might want to make is not true. Like if you just make it like the arbitrary decompositions, then it won't be true.
I'm not surprised it's not true, because it would be amazing if you could assign an area to an arbitrary center
exactly.
of the Hilbert space.
So I had a question. I'm not completely sure if it makes sense. Yeah, you were talking about this picture with basically the bulk legs. If I have a situation where, just the simple situation where I have a tensor network and I don't have any bulk legs, I'm just wondering the definition of area you gave. What does that end up telling you in that situation if I take a part of the tensor network?
Good. Okay, so yeah, there's sort of two things that you're bringing up here. One is that, like, if I now consider my isometry to be a tensor network, it has its own definition of area. How does that relate to ours? And then another is like, you just fixed the bulk state. So just fixing the bulk state, like removing the bulk legs, so it's effectively the bulk state. That works just like that. That carries over. It's like you fixed the state psi. Okay. The fact that tensor networks have their own definition of area is a very interesting point, and it's we can prove a lot of very important relationships between our definition and the tensor network definition, but they're not always equal. Mm-hmm. Like our definition does not in general equal a tensor network area for a general surface. However, here's a claim I'm making, which we can prove. They are equal for all quantum minimal surfaces, and for other surfaces that aren't ever quantum minimal, our definition lower bounds the tensor network definition. So our theorem is like implies a quantum minimal surface formula for tensor networks, to the extent that there is one, and is stronger. Yeah, it's stronger than it. So
I see. Thanks, Daniel.
Yeah. So I'm not sure if this is right, but let me try to suggest an alternative way of saying the same thing, which is maybe closer to how I was thinking about it before. So when you talk about this state specific or subspace, reconstruction, of course, one thing you could do is you could just take a subspace and say, now that's my new code subspace. And I'm just going to ask what, standard reconstruction has to say about that code subspace, right? So I can clearly do that operation. Yeah. But if I understand, I think you're doing something a bit more, which is that you want to restrict to subspaces where I take some state that I like, and then I take all the states I can get by acting on that state with local unitaries.
Exactly.
And so I think if I take that subspace, then your reconstruction is the same as mine. Maybe I'm wrong. I didn't check it, but that seems plausible to me.
Yeah, you're right that in this exact setting, this reconstruction actually is strong enough to imply your sort of reconstruction. But when you add in the errors, it's no longer equivalent.
Well, sure, because my theorem was exact. So once you put in errors, it's not going to be my theorem. But
right. Well, there is an approximate version of your theorem, as you know.
Yes.
And there's an approximate version of this theorem. And it just happens to be that the exact versions are equal, but the approximate versions are not, and that this one's much weaker. That's, yeah.
Yeah, I could imagine that. Is there a big difference when the code subspace is small, or the difference in the approximate setting is only big if the code subspace is big?
Yeah, when the code subspace is big, because if it's small, then the error is sort of like the problem.
Errors can't matter too much, I guess.
Yeah.
I bet that they're still close to each other when the code subspace is small, but I wouldn't be surprised if when it's big that they become fairly different.
Yeah, I agree with your expectation.
I think Jeff was saying something too. I don't know.
Yeah, I was just going to say, Daniel, that it's not like having a code subspace that consists of your original state plus any product unitary acting on the original state. It's the original state plus one particular product unitary, right? Because we're only wanting to do one particular product unitary at any given time. Right. It's like your original state plus your like target state.
But let's see. I mean, wouldn't you, even if you allow yourself to do more product unitaries?
I think if you can do any product.
Won't it still not change the entanglement wedge, right? Because it won't change the entanglement and it's all space-like separated from the area.
But the span of those states, like if you looked at the span of all the states, then it will.
True. Okay, true. Yeah. Okay.
That's how you do it.
Fair. Yeah. Okay. So I pick one and then I take a two.
Yeah, exactly.
Code subspace, and then it's the same. Okay, I see.
But yeah, exactly. And what I was saying was that if you have no error, then you can start adding them together and then building up your very strong reconstruction.
But you can imagine and you're allowing the reconstruction to depend on the state. So maybe if you try to take an intersection of two-dimensional subspaces, you might want a different reconstruction. I'm not sure.
Yeah. So the going from the exact thing to your thing, I think in the most general case, we don't have a proof that our sort of reconstruction extends to state-independent reconstruction. In simple settings where you just have sort of say one bulk leg or something, then it definitely does. But yeah, and we don't know any non-trivial exact examples, interesting non-trivial ones. So we think it probably does, and you need the approximate one to get interesting things. But I think that is technically an open question.
Thank you.
Edward, did you have another question, or was your hand raised from before still?
No.
Okay. So then Tom, go ahead.
Hey, yeah, so I have a question about whether you can reconstruct just arbitrary, say, bounded operators. I guess you can do that locally, but can you make a statement about how you can reconstruct in more non-local regions?
Yeah, you're talking about like consider things that aren't
unitaries.
Yeah. I'd have to think about that, but I think that if you can do things like change the entanglement between, if you have a setup like this, or you have B, there's two candidate minimal surfaces, and let's say this upper one is minimal because of some entanglement between these regions. If you are allowed to do operations that weren't product unitaries, like certain operations that aren't product unitaries could, for example, map this to a state like this, where you just take all those belt pairs and you turn them into factorized states, removing the entanglement, changing the entanglement wedge to this guy, which is...
But somehow if you're limited to only acting within some small region, then maybe you can... Like it's still somewhat local, but not.
Yeah, I mean, certainly there's no problem if you can only act in this region. Yeah.
Okay.
Tom, just to add one more comment to what Chris said there, I'm not sure if this was what you were saying or not, but one definition, nice sort of like operator, Heisenberg picture definition of quantum error correction is like that you have a boundary operator that has the same expectation value as your bulk operator, right? But certainly in the case where you only have one bulk state, then that's sort of trivial because you just define your boundary operator to be the expectation of your bulk operator in that state times the identity operator.
Right.
And that clearly has the right expectation value. So because we're only considering a single state, then the definition in terms of what you can do with a unitary is the sort of nicer one that,
Yeah,
real
sure.
one.
Sure, I guess if you have a reference, you can do a bit more, I guess. But,
yeah, but
Yeah, well, okay.
We maybe talk about this online. I
Sure.
think there's maybe some interesting things to say, but yeah,
Mhm.
it's a bit trickier to work out what the definition you wanted.
Sure.
Let me ask, may I ask a question? So
Yeah, please.
I cannot raise my hand, sorry. So do I understand correctly that what you're saying is that you can do, when you have a quantum extremal sources prescription and so on, the sense in which you have reconstruction is that you can add, let's say, a probe qubit, or you can modify the state of just one qubit, and it's that you can recover. Is this an alternative way of saying what you're saying, or is it?
Yeah, effectively. But that's what you're guaranteed to be able to do. You might be able to do something stronger.
You might have something more, but that this is the sense in which entanglement wedge reconstruction
Yes.
works
Yeah.
in general. Yeah.
Yeah. Okay. That's.
Thank you.
Any other questions or comments? Okay, well, if not, let's thank Chris again, and we can get Jeff set up.